Good morning, everyone. Can you hear me? Yes. Okay. Welcome to the tutorial for B5. Can we please have everyone's attention? Welcome to today's tutorial for Study Committee B5. The topic of today's tutorial is applying synchrophaser technology for protection of the power system. With the changing power system and the behavior of the power system, increasingly synchrophasers are becoming a necessity, and several applications have been introduced into the power systems around the world. So the format of today's tutorial will be as follows. We will have an introductory presentation just onto the subject of synchrophasers. This will be followed by the work of one of our working groups that recently completed their work on synchrophasers, and this is working group B5.62, and so there will be a report from that working group, and thereafter we will have a couple of applications from this region, various applications of synchrophaser technology. Just by way of introduction, my name is Anita Uman. I am currently the convener of the tutorial advisory group for B5. I am from South Africa, work for the power utility Eskom in the transmission system operator. So that's just about me. So I will introduce the first speaker. The first speaker for today will be Mladen Kezanovic. Mladen has been with Texas A&M University for 35 years, where he holds the titles of Regent Professor, Eugene E. Webb Professor, and Site Director of Power Engineering Research Center Consortium. He's also the principal of Expert Power Associates, a consulting firm specializing in power systems data and analytics for the last 30 years. His expertise is in protective relaying, automated power system disturbance analysis, computational intelligence, data analytics, and smart grids. He has authored over 600 papers, given over 120 seminars, invited lectures and short courses, and has consulted for over 50 companies worldwide. Dr. Kezanovic is an IEEE Life Fellow and a Seagrave Fellow, honorary and distinguished member. He's a registered professional engineer in Texas and a member of the U.S. National Academy of Engineering. Please welcome Mladen for his presentation on the concepts and introduction to synchrophasers.
Thank you, Anita. How do I get to the slides? I guess I just click next.
No, that'll be automatically.
Oh, automatically. Nice. Okay. While they're doing that, good morning, everyone. I hope you enjoyed the conference. It was really exciting to see so many people attending and so many topics covered, one of them being synchrophasers. So that's good. So my job is to give, in 10 minutes, a brief overview of what this area is all about. So it's going to be a little bit of a challenge, but we'll try to work on it. So the outline is, as you may see, eventually. Oh, it goes one by one. I will be covering the technology very, very briefly so that we all know what we're talking about here. Then I will be covering developments in phases. And this is arbitrary. I have divided the phases in a particular way, in particular year intervals, and I'll give you the reasons why I did that. So the phase one was expectations, what people were expecting when these things were introduced. The phase two was realization, deployments and things like that, and phase three is the future. And then I'll have a few conclusions. So technology is summarized here. On the left-hand side, you see phasers, and the term synchrophaser relates to phasers, obviously. But the word synchro is quite important. It's synchronized to the time reference. And on the right-hand side, far right, you see the typical front end of an instrument that samples the waveforms and then eventually calculates phasors and some other things, frequency and so on. And you will see something that is shown as S/H, which stands for sample and hold. So when you're going from analog to digital, you have to sample first and then convert through the A to D conversion into a word, a digital word. So sampling is time synchronized from the GPS clock. And so the GPS clock is received through the receiver, which is at the bottom of that picture. And the receiver has two outputs, has something that is called pulse per second. That's the clock that is actually used for this sample and hold. So all of the PMUs across the system would sample at the same time, driven by this clock. The other input or output of this input to the algorithms is the actual absolute time, whether it's a UTC or recalculated to your local time. So it's basically a time stamp that is assigned to each sample. And you know exactly to the time reference that is common across the world where that sample was taken. Now, the other pictures are showing two other concepts here. One concept being that once you start sampling and time stamping, it depends when did you start that and what's your reference angle. And so typically in the applications in utilities select a given bus to be a reference bus for, let's say, a voltage signal, and then all of the angles are calculated with respect to that bus. And the last point down at the bottom is related to what is called reporting rate. A lot of people confuse, this because the title is confusing of the PMUs. PMUs are not phasor measurement units. They are phasor calculation units. And they calculate from samples and they report at a certain rate, whether it's a 60 times, 120 times, or whatever per second. So that brings us to the next part of the technology, which is how are we doing with the standards and how these PMUs actually do appear in terms of devices. So on the left-hand side, it's just something that I picked up from voltage measurements. It doesn't matter what it is. But the front end for SCADA system is a remote terminal unit, as you know. However, in the substations, we have potentially standalone PMUs or PMU algorithms embedded in other devices, like protection relays or digital fault recorders and so on. So that's what is shown on the left-hand side. The issue remains, how do you integrate all of these samples and eventually measurements into the control room, for example? How do you put it into the SCADA database and applications in the control room? It doesn't have to go to the control room, incidentally. You will see that from some other applications. It can be a special protection system that just takes inputs and issues outputs to particular breakers, never goes to the control center per se. I'm not going to go over standards. The issue is that the standards have evolved over time. We have standards for many things, primarily PMUs, PDCs, concentrators, as well as testing and evaluation, and it propagated to the IEC 61850 as versions of these standards. So we are well covered on the basic stuff, very basic stuff. I want to bring to your attention that we are not covered at all to the extent that we need to be with the standards. But we have the basic standards in place. Now, moving on, those are the phases. I picked up 2008 to 2015, quite arbitrary, as I said, because this chart to the left-hand side comes from Gartner. I don't know if you're familiar with Gartner. They have this hype cycle for any technology, and you will see the phasor measurement units going up, which means expectations were very high, but typically after expectations are kind of exhausted, if you will, and reality kicks in, then the interest goes down, and then eventually the technology that survives picks up and goes on. In 2008, the predictions were quite high. It's going to solve all of the problems in the world. realization came later on, and we realized that it can be used for certain things and it may not be used for some other things. In the United States, where I'm coming from, we had some major developments in that time interval. In 2007, we have something that was called ESA Act of 2007, which was the first act across the world that defined the smart grid, Article 13 of that act. You may go out of curiosity and check that. In 2009, we have what was called AARA, American Recovery Act, where the government offered 50% investment in synchrophasors to the utilities if they would match. So we have a massive deployment of PMUs since then and up to 2015. On the right-hand side, there's some of these. Just to give you a flavor, Texas alone, which is a standalone system, today has about 250 PMUs. It's about 5,000 bus system. So note something, even though we have thousands of these in Australia, not thousands necessarily, but potentially, but in China, in India, we're picking up in Brazil and United States and so on, they are still very sparsely located in a given system. You are talking about a few thousand of these units in a system of 70,000 buses on the Eastern Interconnect or 25, 30,000 or whatever on the Western Interconnect. So anyway, that's what's happening in that, what was happening in that period. Now, we are in this period now, and I have one example from a utility company that shows how they are managing different applications, putting in integration with the control center and so on. I don't have the time to go into these applications, but one very common application is state estimation, because if you can directly measure the voltage and the angle, then it's so-called linear state estimator. There are several companies offering such products today. On the right-hand side is who the users are these days, or domains. Operations, certainly, because synchrophasors give, call it measurement or calculation, every, let's say, 60 times a second. SCADA is way out of that range with many, many seconds in between the scans and so on. So this is the best you can get in operations to monitor signals. Now remember one thing, because it matters a lot. This is primarily developed for monitoring phasors or deviations from phasors. And when we come to transients, real transients like faults and transients caused by inverters and stuff like that, the synchrophasors are having difficulty following some of these things. And there are some other developments along those lines that will take care of that. So that's that period. And then we're now looking at the future. And I picked up, 24 to 34 arbitrarily again. And maybe this is the most interesting part, because that's what's ahead of us. And we all are trying to figure it out and, use it and so on. So one development is so-called point-on-wave recordings. People invent terms, okay? We had point-on-wave, God knows when we had, relays and recorders and whatnot. But here we are dealing with two different things. One is, it is streaming data, not triggered data, like in relays and recorders, A. And B, it's time synchronized. So that's a huge difference. How are we going to deal with the amount of data? That's a different story and very important story to tackle. If you start looking at the streaming data, what are you going to do? Most likely, you're going to have to look at automated means of managing, storing, and analyzing. Automated means. There may not be manual if you're going to use it for protection operations, stuff like that. Embedded designs, there will be new designs, they're already on the market, where you have a platform that actually does the point-on-wave, continuous, and then you have applications building on the top of it, whether they are synchrophasors or something else. And then eventually, people are moving these things to the cloud. Several companies in the United States are already doing some of the functions from the control center in the cloud, shipping synchrophaser measurements there. We're going to have to learn how to do real-time simulations to compare certain things from measurements to models and simulation in real time. Digital twins, meaning modeling the whole system in software. correlation with other big data, weather, lightning detection systems, and so on. That's not done necessarily today as much, and it needs to be done. Now, applications, again, we're going to see them in the EMS, at the transmission, ADMS, microgrids, protection, particularly wide area, monitoring of IBRs. This is a very, very important item, as you know. At least we know very well in the United States. We have reports from NERC about several issues in California, in Texas, and so on, where IBRs misbehaved and caused a major tripping in the system. And there's no way to figure it out, really, unless you have recordings. And so people are scrambling how to record all of these things and talking about the point on wave for recording. Then interaction that the inverters may have with the protection, and monitoring of low-frequency oscillations. Low-frequency oscillations started with the sub-hertz, and then the wind and everything else came in, and we see 7 hertz, we see 13 hertz, we see 15 hertz, we see, it just goes on and on depending how these interactions are developing in the system. And finally, asset and outage management. With this, I will come to, this meant 1 more minute? Oh, 2 more, okay, very good. Great timing. So time synchronization is here to stay. It's not going to go away. So we need to think about it. I'm pretty sure everybody had thought about it that has systems in, but there are many, many things that haven't been tackled yet. I'm talking about, the standards that still need to be developed. I'm talking about this point-on-wave stuff. I'm talking about large amount of data that requires, machine learning, data modeling, and so on. So all of that is quite relevant. As I said, the synchrophasors are kind of gradually moving from transmission to distribution, and from synchrophasors to synchronized point-on-wave. So those are the major trends that are happening there. Then we have embedded devices, meaning everything these days that you can talk about is from smart meters to recorders to embedded controllers on the circuit breakers. Anything like that people are thinking about, they're already doing time synchronization of the samples that are taken there. So what we're going to see is not PMUs. We're going to see a bunch of these devices across transmission, distribution, microgrids that inherently inside have capability of synchronized time synchronized sample collection and calculation of the quantities that you may wish to calculate. And then finally, we have, as I said, broadening across domains. Now, this is an important part, and I will close with that. SIGRE has different colloquia and so on, had different working groups. I would like to bring to your attention SGSMA 2014. That's the flyer that some of you picked up. If you didn't, there's a flyer here. It's the first conference that is jointly sponsored by IEEE and SIGRE. So it takes place next year in May. And of course, there's always NASPI, North American Synchrophaser Initiative. With that, I'm sorry I went 1 minute over, I think, but thank you very much for your attention.
Thank you, Mladen. Our next presentation will be the summary from Working Group B562. The title of the presentation is Life Cycle Testing of Synchrophaser-Based Systems Used for Protection, Monitoring, and Control. The presenter for this topic will be Ritesh Bharat. Ritesh is a principal engineer at PowerCore, and he has over 25 years of experience in the field of protection, automation, and substation design in Australia, New Zealand, and Asia. His main areas of interest are non-conventional instrument transformers, process bus, and phaser measurements. Ritesh is a Fellow of Engineers Australia and member of several SIGRE B5 working groups, and has presented papers at many international forums on topics such as digital substations, wide area monitoring, dynamic line rating, rapid earth fault current limiters, traveling wave-based fault location, etc. Welcome, Ritesh.
Good morning, everyone. Back in 2017, this group B5.62 was formed, and we had members from all across the globe. Mladen was the convener, and we were basically looking for what sort of testing is required for life cycle of synchrophasor-based or wide area monitoring protection and control systems. So you can see on this slide the first page of the technical brochure and the name of the members on the right. Now, my presentation will it's okay, it's working. Yeah, so it will cover why testing is so important as part of a life cycle management of any product or system. What was the purpose of forming B5.62? We also had, because of the inputs from, due to the inputs from the members, we were able to get a lot of data from different countries on what sort of testing methods are adopted by different countries in the world. And I have chosen 3 countries to share their experiences. And this was basically their own method of testing the systems due to lack of international standards on testing. Then there is there was a lot of study on what sort of future PMU technology developments are happening in the world and why is it required. What are some integration requirements? What are the life cycle testing requirements and the recommendations of the report. So the basic purpose of forming the working group was to find out what are the existing PMU and synchrophasor system standards. You must have seen in Mladen's last presentation. There was a list of standards available at the moment. What is the importance of the concept of interoperability and why it is important? Why certification may be required, and then who is authorized to do those tests? How certification is accomplished, and obviously most important thing is the cost associated with it. What are the acceptance, commissioning, periodic maintenance, and troubleshooting test procedures? Why such life cycle procedures matter and how they are implemented today? And how to plan PMU certification and life cycle testing. So let's look at why testing is important for life cycle management. So we can divide that into 4 main parts. First is the acceptance, or you can say the compliance to the standards and specifications. It is very important to test the device or system to the international standards and any specific client requirements. Then comes the commissioning testing, because many devices which work fine independently can cause trouble when tested as part of a system. Once the system is commissioned and running, periodic testing is paramount to ensure that the data being received is accurate and reliable. And if there is any malfunction in the system, then troubleshooting maintenance or troubleshooting testing must be done to get the system up and running as quickly as possible. Now the benefits are huge. It increases the lifespan of the system. It helps maintain continuity. It provides better efficiency and also acts as a good lessons learned, you can say, for future projects. And it can save a lot of money. So why we say life cycle? I'm using the term life cycle many times. And if you see this wide area monitoring architecture, you can see it contains many components. So you can have phasor measurement units which are as standalone units, or they can be inbuilt as part of the digital fault recorder or a distance protection or any relay. Then they're all connected to GPS. They have got via switches and routers, they get connected to the PDCs, and then via gateways, they get data is transferred to the control center. So there's a lot of individual devices in the system, and there are standards to actually test them individually. But to test from one end to another end is a challenge, because there are so many devices, and there's no international standard for testing it, and nobody, like individual manufacturers take responsibility of their own product, but they don't take responsibility of the whole system. So ultimately it lies, the responsibility lies on the client himself. So I'll be sharing 3 examples of what clients globally have adopted to test their systems. The first example I'll be taking is from India. So this was a specification for a project called URTDSM. That is one of the, to my knowledge, it is the largest project in the world, with more than 3,000 PMUs sending data to the control center. So if you look at the right-hand side, it says that after field testing, PMU shall exhibit 98% availability during test period of 500 hours. So this basically, by saying this, they have tried to ensure that right from the CTVT to the control center, everything is tested. Also, point number 5 and 7, which I've highlighted. So they have tried to ensure that the PMUs are communicating with the PDC and with the GPS. So these are methods adopted by the Indian utility to ensure that it's tested properly. The next example is from Finland. So on the left-hand side, you can see a RTDS simulator software, and then through amplifiers, it goes to PMUs, and then to the PDC, and finally to the control center, or to the application. So by testing, by simulating data from the RTDS, measurement values from the RTDS, and checking it on the application software, they ensured that the measurement accuracy is within international standards IEEE C37.118. Then the next example is from Brazil. You can see the columns first, second, and third. So this is actually the attempt taken by the PMU to actually fall within the accuracy requirements of the IEEE C37.118 standards. So if you say, for example, ID number 3, the PMU failed on the first attempt, but then there were some software or hardware modifications done by the manufacturer to make it compliant to the accuracy standards. And then it passed in the second attempt and the third attempt. And on the right-hand side, right column, you can see what sort of measurements were taken. Finally, their approval method is shown on the smaller table, where they have listed the vendor number, the particular model, mainly the hardware side of it, what firmware it had, and the results. And you can see that the vendor number 6 passed on the metering side, on the metering with M class, did not pass on P with the firmware, with the hardware A, and then with hardware C, it passed even with sample values. Now let's see what are some advancements in future PMU technology. Now, no matter how good a PMU is, the data accuracy will always depend on the accuracy of the instrument transformers. Hence, it is very important to have precise measurement at the source. You must all have heard about optical instrument transformers. So they are actually the future of power industry measurement technology. Optical sensors convert light rays into electronic signals and convert it into a form that is readable by an instrument. Their output is highly accurate, current and voltage, providing electrical isolation, linearity, and temperature stability, and having great potential for future applications. Compared with PMUs connected to conventional CTs and PTs, CTs and VTs, the optical PMUs will be immune to electrical noise with higher measurement accuracy and more tolerant to solar magnetic disturbance and electromagnetic pulses. In order to assess the operating condition of the grid in real time, predict behavior, and to respond to events, PMU should be capable of achieving fast and accurate measurements during transient conditions. Most commercially available PMUs are based on discrete Fourier transform with 2 to 6 cycles for phasor estimation. Their dynamic response accuracy is not accurate to capture system transients to initiate control actions to stabilize the grid. PMUs with adaptive window size technology and instantaneous phasor estimation algorithm will enable transient capture and prediction. Similarly, devices with high reporting rate will provide more observation points to extend power grid visibility during transients, dynamics, oscillation, first swing, frequency instability, and voltage instability. High data rate also allows for dynamic response prediction and increases the accuracy of power system model validation. The increasing number of power electronic devices for renewable generation has increased the quantity of nonlinear components and harmonic distortion. Hence, it is of great importance to measure the level of harmonic distortion accurately for the reliable operation of power systems. PMUs have been used in distribution level, which has significant harmonic content. Including odd and even harmonics in PMU will provide the grid operators better visibility of the power quality issues. The harmonic analysis also can help better understanding the impact of harmonics on the system and the service, and how phasor measurement calculation is tempered or influenced by the harmonics. Furthermore, analysis of power spectral density can be further applied by combining the calculation of interharmonics and harmonics to study the noise level of power grid and effect of noise on phasor measurement accuracy. We all know how critical GPS time synchronization is for PMUs. So PMUs rely completely on the GPS. So any loss of GPS signal can render synchronized measurement-based applications meaningless. Equipping PMUs with alternative or backup timing source can be effective solution for reliability improvement. Connecting PMUs in existing circuits can be challenging sometimes, and portable or non-contact PMUs can also be a good solution to check healthiness and accuracy of the circuit. Multifunction devices that combine phasor and power quality values such as harmonics, voltage, sag, swell, signal to noise ratio, and voltage flickers provide better value. PMUs can also provide point-on-wave data. Hence, PMUs integrated in comprehensive power system monitoring units will provide a better value proposition. Let's look at some of the integration requirements. So, firstly, there are so many manufacturers of PMUs. It is very important for them to be interoperable, and so that if required, one PMU can be replaced with another PMU of a different manufacturer. Ideally, all PMUs complying to C37.118 should be interoperable, but in practical experience, we see that we always face some sort of challenges. PMUs claiming to comply to a standard can have variable acceptable limits, such as complying only for P class or M class, complying only at certain frames per second. Hence, it is important to get PMUs calibrated and certified based on specific requirements. We have already seen the benefit of end-to-end testing due to non-availability of standards. Solutions will have to be defined in terms of subsystem-centric standards. Backward compatibility is also important to enable new devices to work with the existing systems. Now, the examples we saw from different countries, we have seen that each one of them have deployed evaluation methods to test their specific requirement using commercial test tools such as Omicron, Fluke, or Double. But having a standard to define the requirement for life cycle testing will actually make evaluation much simpler. In the recommendations of the report, we recommended the following. So, Chapter 6 and 7 of IEEE 37.242 standard should be followed until a dedicated testing standard is released. End-to-end testing practices should be better defined. Although synchrophasor technology has been in existence for some time now, there is still a need for trained staff, especially for testing. This technology has not been utilized much in the distribution network, and a separate working group should be formed to develop and address challenges which are unique to distribution. Now, the future steps, PMUs should not be considered as a product, but as a part of a wide area monitoring, protection, and control system. And testing requirements should be defined from a system point of view. Vendor support is very critical to test interoperability and to address key areas of improvement. Standards should be developed to perform end-to-end testing, and more research should be done to test performance of WAMP systems under transient conditions and recommend suitable test procedures. Thank you.
Thank you, Ritesh. Our next presentation will be by James Guest. The title of the presentation is Market Operator AMO Wide Area Monitoring System Synchrophasor Project and Associated Standard Data Guidelines. James is a senior engineer working in AMO's operational analysis and engineering team. During his time at AMO, he has worked in grid and SCADA modeling, operations planning, national planning, and congestion modeling. James has experience in power system modeling and real-time analysis, applications, and systems. He has an interest in automation and has developed several decision-making tools currently in use across the organization. Please welcome James.
Thank you very much. Okay, just a bit of context about what problems we're trying to face here at AMO. So for those of you not familiar with the East Australian grid and AMO is the independent system operator for almost all of Australia, but my team specifically looks at the east coast of Australia, which is the largest interconnected power system in the world by geographical size. So from the top to the bottom, over 5,000 kilometres, it's simply massive. But despite that massive size, it's quite a small capacity, only about 50 gigawatt system, which gives us a lot of unique challenges that aren't really seen many places else around the world, particularly very distinct inter-area modes of oscillation. So our system is actually unstable without active dampening on our system for those inter-area modes. We've got a very high penetration of inverter-based resources, particularly in very weak areas of the grid. And we're seeing many never-seen-before challenges, such as issues with low system strength and low inertia, that are really challenging the way we have to manage and operate the grid. So as I said, because of the long nature, we've got this oscillatory stability problem, this oscillations between different groups of generators in the states. The oscillations are usually on the order of, 0.5 to around 2 or 3 hertz. And we have lots of loads, power system stabilizers on generators, oscillation dampers on SVCs to help us manage the problem. But as the synchronous generators become decommitted, as they retire, we lose that oscillation damping on the system, and it's a service that isn't currently provided by inverter-based resources or batteries at the moment. And probably one thing to note is that this is probably one of the largest leading causes of blackouts in the world, this oscillatory stability problem. So it's something we're very concerned about keeping it under check. The other problem, another massive problem that we're starting to see is system strength issues. So system strength is really how susceptible the grid is to fluctuations in voltage. It's particularly an area of concern in areas with high levels of IBR, inverter-based resources, because in those low system strength areas, they can become unstable. Synchronous generators provide system strength services and help stabilise the grid, but again, as they retire, we get more inverter-based resources and the overall grid strength becomes weaker. And of course, inverter-based devices, as they are currently, they do not provide some of these system strength services. We have a lot of very weak areas of the grid, but in particular far north Queensland, where we are now, and in the south, down in Western Victoria and parts of South Australia, very, very weak systems. Now, why is this a problem? Well, controlling inverter-based resources is a challenge in weak systems, and the way system strength issues manifest is as voltage oscillations. So you can see there on the graph, that's an example of an inverter-driven oscillation at about 17 to 18 hertz. And the problem for AMO is that these kinds of things we're completely blind to. You can see there's a light purple line there. That's what the control room would have seen over their SCADA systems. You can see it's completely hidden the issue. So we're completely blind to these issues. We do not see them just due to the nature of the SCADA systems. The oscillations have been proven to exist through extensive simulations, modelling, and fault recorder measurements. So we know they're there, but we have absolutely no visibility. And I probably don't need to be the one to tell you, but visibility really is critical to operating the power systems. Our SCADA system feeds into so many services, and if the SCADA system isn't working or isn't up to requirement, then we have a serious challenge managing the power systems. And there's many reasons why the SCADA system might fail, but the one that's most concerning is probably this one here, the unseen phenomena. So not being able to see the issues. So we just don't know what we don't know. So how have we tried to address it at AEMO? Well, we've started to increase our rollout of phaser measurement units, and there's a bit of information which is mostly what Mladen talked about earlier. But the main thing is that for AEMO, we're really looking at increasing our penetration of these PMUs. So we've set up a project with the NSPs to really rapidly deploy as many PMUs as we can in critical areas of the network. And you can see there's a diagram of our committed rollout of PMUs. We're sitting at about a couple of hundred channels at the moment, but we're expecting to roll out up to close to 1,200 channels on the system. To facilitate this, we've also come up with a naming standard and guidelines and standards around PMUs and what the minimum requirements are. Obviously, we can't say we want a specific PMU to be installed at any given place, so we've leaned heavily into the standards, so the C37118 2014 standard for accuracy and reliability, and as well as things like coming up with naming standards so that we can easily identify and expedite connection and integration of the PMUs into our system. So where do we go from here? So AEMO is really leaning into next generation real-time analytics, using these devices in real time to give both control room operators an understanding of what's going on the power system, and both offline staff as well, for basically whatever the imagination can think of, for fault event analysis, for oscillation detection. The sky's the limit. It's really just up to the imagination. So this is one of the applications that we've been looking at. So looking at oscillations, as we mentioned, for those system strength issues. We've got a tool in place at the moment that's monitoring oscillations in the system up to about 25 hertz. So our tool has been able to use PMU data to capture those kinds of oscillations and alert us in real time when something like that is happening, and it's been very highly successful since we've been implementing it. And our next development that we're currently looking at is actually, now that we know we've got an alarm when the oscillations are happening, what do we do next with that information? Well, there's a neat little algorithm that's being developed by ISO New England that will actually use PMU data to narrow down to exactly where the source of the oscillation is coming from. And we've been testing this algorithm on simulated and real data, and it's been shown to be highly effective for these kinds of inverter-based oscillations to narrow down exactly which plant is causing the oscillation. You can imagine that from there, once you've got that information, you could take actions such as directing the unit to reduce their output, to reduce the oscillations, or worst case, tripping a breaker to take that plant offline if you knew exactly which plant was doing it. But the current issue is that we don't know which plant is causing it, so we preemptively constrain all the generation in the area, which is obviously suboptimal for the market. So we really have two future challenges when it comes to synchrophasers at the moment at AEMO. It's how do we use the data online and offline? How do we make the best use of it? It's really great information, but we really want to take full advantage of it. So we really need to think about how we can effectively use and understand this data. And the second, even more important, is once we have a result from whatever analytics or applications that we have, what action should the control room take? Because it's all well and good to give the control room a nice pretty display with a wiggly line, but if they don't know what to do when something happens, then there's no point. So really, we need to make sure the control room knows what actions they need to take when something has been identified. That's the end of my presentation. Thank you very much.
Thank you very much, James. The next presentation we have is titled South Australia Wide Area Protection Scheme Synchrophaser Application. associated with increased renewables and interstate connection. The presenter will be Philip Ivanovsky. Philip is a technology manager at CSC Uniserv. He manages CSC's protection and control systems portfolio. He has more than 10 years experience in application support, detailed design, testing, troubleshooting and commissioning of power system protection and control schemes. He has an interest in digital substation design and special protection schemes. Philip holds a Bachelor of Engineering Honours and Bachelor of Commerce degrees from the University of Melbourne. Please welcome Philip.
Okay, morning everyone. My name is Philip Ivanovsky. Before we kick into the slides, I'd like to acknowledge my fellow authors, Davinda Pereira from Electronet and Sean Norris from GE. So let's begin by looking at the problem, or rather I should say, the motivation for developing and deploying such a scheme. And really it all boils down to South Australia's transforming power system. So on the map there, James spoke about the NEM network, the Eastern Seaboard, but you can see South Australia at the end of a rather skinny, stringy network, over 5,000 kilometres of line, and mainly radial if compared to other networks around the world. And you can see the long transmission corridor connecting the inertia zones in Victoria and South Australia. And South Australia's inertia tends to vary widely with the amount of renewable generation, and that's been trending downwards over the years. We've seen coal-fired generation decommitted, and we've seen South Australia's got world-leading levels of rooftop solar, as well as the continuous development of grid-scale solar, wind and BESS coming online. So really good dynamic data is critical to understand and improve the resilience of South Australia's system. System security and reliability is critical as South Australia transitions to low carbon emissions future. So take note of the event there on this diagram in 2016, a statewide blackout. So South Australia is prone to severe weather events, ranging, from storms to tornadoes, and that's unfortunately what happened on this day in 2016. Tornadoes ripped through the state, and this affected 3 275 kV transmission lines, resulting in 6 voltage dips in a span of about 2 minutes, and this affected the protection and a lot of wind turbines, and large amount of generation tripped off, about 460 megawatts. The Haywood interconnector tried to pick up the slack, and the protection there, loss of synchronism protection was activated, resulting in the islanding of the state. Subsequent to this, some thought was put into developing a system integrity protection scheme, and you can see there the scheme itself incorporated 3 discrete progressive stages, and the stages were intended to operate in an escalating manner so that the outcome from the preceding stage was intended to defer or prevent the onset of the next stage. And this varied from triggering of BESS to load shedding to islanding the South Australian system. This scheme works. There's been successful SIPS action in the past, but a reassessment of the scheme against an EMT model of South Australia, there was some shortcomings found, particularly in maybe load shedding too much, or sometimes the stage 2, the power swing, not operating when it should have. So there was the next step was to review what other technology is available and how we could possibly upgrade the scheme. So that's when we embarked on this journey. It was a pilot project for a synchrophaser-based wide area protection scheme. And following the successful conclusion of the pilot project, the WAPS was developed, and it utilises a three-pronged approach. So there's triggers for different types of grid stress, including, as you can see there's function blocks for network stress, so angle and frequency difference for an emerging angle stability event, power imbalance. So the power imbalance is used in two ways. It's used to trigger, but it's also used to determine the volume of response that's required, so a proportional response. And then there's a system event. So this is for more severe events, as large and fast frequency changes and rock-off drops. So the scheme itself is bidirectional, so it can work irrespective of whether South Australia is importing or exporting. But for now, it's only active when South Australia is importing power from Vic. It's the functional block diagram of what I described. So there's two tasks running. There's the fast scan task, which is executed every 20 milliseconds, and that has the event detection processes built in, and then there's a slower scan task, which is an interface to Electronet's EMS, and that's getting data on the battery charge, the sheddable load level, the generators that are online to calculate the inertia level. And the response is either level 1 or level 2, so level 1 being a best discharge only, so there's a BESS array that's built, there's a BESS stack, and then for more severe events where level 2 is justified, then we'll look at load shedding as well. So here's the slightly complex overall system architecture. You can see the PMU placement is spread across the state. There's 5 locations. There's 23 logical PMUs that are being streamed from these sites to the scheme is redundant, so to controllers at 2 control centres. Those controllers have an onboard PDC that's forwarding the data internally to quite a powerful PLC engine that executes in hard real time, but it also forwards to a wide area monitoring system. So if the control scheme was to operate, it then triggers via Goose. There's a protection relay that decodes the Goose and then hardwires the trip signals to tripping devices, and then they're sent downstream via a multiplex C3794 network. So a little bit about the implementation, testing and tuning of the scheme. There was a number of libraries, case libraries that were prepared to simulate complex multi-event simulations and to help with validating and tuning the scheme. There was an open loop testing was conducted mainly for determining trigger accuracy and validating the hardware. So that was at Electronet's engineering evaluation facility, where they have an RTDS simulator, and that would play back the data and validate the scheme. And there was also a subset of closed loop tests for response to the control action that was taken. Since then, real code simulation models have been developed of the controller and the logic that runs in the controller, and that's been useful to validate the power system model from the FAT results, and then also enabling further closed loop testing to take place. I'm going to skip over this slide because it's just the benefits that we see of WAMs and WAPs. Needless to say, it helps, WAPs provides a generalised response to complex disturbances, and the responses are proportional to the event. The next step, so the scheme is evolving. This isn't the end. There's currently a second AC interconnector that's going in, Project Energy Connect, so Electronet working with Transgrid, building a double circuit interconnector, and the scheme will evolve to take that interconnector into account, and this special protection scheme will then be required to detect the non-credible loss of either the Haywood interconnector or the PEC. And this time there's going to be a hybrid approach taken. So there'll be an event-driven component, which will be a topology-based scheme, which won't monitor power flows and just monitor the statuses of the double circuits of the key corridors. And then the response-driven component that I've already described will be used as the baseline, and it will be developed further. Thanks everyone for listening.
Thank you, Philip. Our next presentation for the session will be by Daniel Moulds. The topic is PowerLink's synchrophaser WAMPAC anti-islanding scheme application. Daniel earned his bachelor's degree in electrical engineering from Central Queensland University in 2012. He's a registered professional engineer of Queensland in the area of electrical engineering. With nearly 20 years of experience in substation control systems, he is currently the principal engineer control at PowerLink Queensland, where his role entails leading the development, maintenance, and continual improvement of PowerLink's design standards and undertaking asset and technical investigations. Areas of expertise include substation control systems, WAMPAC and synchrophaser systems, and IC 61850 systems. Please welcome Daniel.
Good morning, everyone. As mentioned, my name is Daniel Moulds, and today I'll be talking to you about the PowerLink implementation of anti-islanding using synchrophasers. I'll cover a bit of background on why the use of anti-islanding, but then hopefully to give a different perspective, a bit more nuts and bolts detail on how we're actually using the synchrophasers, what you need to consider when you're using, what you may need to consider when you're using synchrophasers to implement some kind of protection and control scheme. The mouse isn't going. There we go. So the background is really when we first started, when we were looking to get our first inverter-based renewables online, we had no clear understanding of how they would react or respond when they're part of an island. So we needed to manage the risk of an IBR exacerbating damage to our equipment or customer load. Additionally, the NER clause that states that for a credible contingency event, the voltage of supply at connection point should not rise above its normal voltage by more than a given percentage for a period of time as per the graph. So over voltage as well was something that we wanted to account for. Typically it's the responsibility of the generator itself, but we wanted to make sure that we were protecting ourselves there as well. So typically, the first response to something like this is to fall back to our business as usual of a status-based scheme of some kind. So what can we wire to a protection relay? What can we send via signalling to wherever needs it to be able to respond? But historically, and I mean most people probably experience this, but while they're reliable, they're fast, they can be very expensive to implement, test, maintain. And when it comes to modifying them, and the way the system's going at the moment, you tee off a feeder somewhere and then all of a sudden you're having to do all this rework, visit all these substations that weren't supposed to be part of the initial project scope, et cetera, et cetera. So the costs can blow out, and we saw that. And when we looked into it a bit more, and there was, I think some of our brethren from the southern states had looked at synchrophases and anti-islanding and had implemented some kind of anti-islanding themselves. So that was the approach we decided to look at, and we originally ran a trial of just a straight point-to-point anti-islanding scheme, and I guess compared to a status-based scheme, that you're looking at the system dynamics, so your synchrophases your scheme's going to be slower. You need to look at grading over protection. So if there is a fault and then the fault clears and everything returns to normal, you don't want to have tripped off a generator when you didn't really need to. So what does that look like? I'll skip over that slide and come back to it. So for example, it's probably a good representation of the area of the system that we were looking at originally. So substation A, for example, that we'll refer to as a reference node. It's a highly meshed part of the system, a lot of generator connections. It's highly unlikely that it would be islanded. And then when you look at the area, so for example, if you look at substation E, if we were installing a renewable air, you look at all the various points along the lines there where the system could be islanded. The scope of any project you're looking at doing there is going to explode, and especially given the way the renewables are working. They're all being installed in similar areas, so you have these zones. So it's not going to be just a one-off. You're going to have to account for the fact that you might have 5, 6, 7 more renewables in that area. So the first installation, so we had our PMU at substation A with a direct connection to a controller and PMU at substation E. You have your comm circuit set up, all the logic residing in the local controller. You're doing your phase measurement comparison and so on, which I'll go in a bit more detail soon. And you do your operation. If you need to add another scheme to the area, theoretically, if you're doing another point-to-point one, you add another PMU at your reference node, and then you generate a bus somewhere else, do the same thing again. But so after our first trial, we went through the process of another project of getting our wide area monitoring protection control system up and running. So the big part of that was that all the control we centralised. I won't go over too much for fear of spoiling what I'm about to talk about in about 2 hours. So for example, our reference node, we have 2 phase measurement units providing 2 voltage sources for redundancy. That information goes back to centralised phaser data concentrators, and then at our generator buses, similarly, we have a phase measurement unit there providing the information back to the regional phaser data concentrators. Those data concentrators pass the information to central controllers. They perform the logic, and then once the islanding conditions are met, the trips are sent to the necessary generator. So give an idea of what kind of logic we're implementing. So basically, there's overvoltage elements at the generator bus. There's some undervoltage protection that takes into account the strength of the reference node compared to the generator bus. And then the main part of it is there's a disturbance detection. So a fault has happened. We wait a period of time for the fault to possibly clear. If the conditions are continuing, such as a phase angle difference or frequency difference between the 2 systems, we'll then operate as needed. So this is kind of the nuts and bolts part of it. I mean, the logic is reasonably straightforward, but when it came to actually looking at how the synchrophases would affect the system, how we need to process them and so on, I guess one of the fundamentals is when you're streaming synchrophases, time is critical, so you want to make sure you're using a sample at the same time period to do any kind of comparison. So, for example, at 10 milliseconds, the arrival of all these synchrophases are going to be asynchronous. So there needs to be a point where you go, okay, something hasn't arrived, you need to move on with life. So, as an example here, at time t equals 0, a 10 millisecond sample at 10 milliseconds arrives from one PMU. A few milliseconds later, a second sample arrives from the next PMU. And then if you need to forward it on, it'll keep waiting until it receives all samples that it's expecting from all PMUs, but there's a point in time where if there's some kind of communications network delay, you need to move on. So typically that sample would be discarded, everything's passed on until it moves on to the next time sample. And another thing to account for as well is previously we'd only really seen PMU samples that were time-stamped exactly on the multiple of the frame rate. So, you know, we're using 200 frame synchrophases, so it'd be 0 milliseconds, 5, 10, 15, 20, and so on. But the PMUs we're using at some points would provide a timestamp that was slightly inaccurate, so you need to be able to account for that and, you know, understand whether or not that's acceptable for your system. So usually it was around 3 microseconds is the maximum we saw, so you need to be able to account for a time variance there so your system doesn't immediately discard it. So I might need to step things up a bit, but so the next part of it is that when you're looking at synchrophases, if you have an overvoltage element looking at 60 milliseconds pickup time, if your synchrophases are delayed, if you're looking purely, if you're typically using an automation timer of some kind, internally 60 milliseconds, there's a good chance that if you're using, if your samples are only 20 milliseconds apart, there's a good chance that if you miss a sample, that timer is still going to time out, but it's only ever seen 40 milliseconds of system data. So what we went with then was that rather than potentially operate early or unnecessarily, we just count the frames. So anywhere where, you know, if we've been told to use a 200 millisecond timer for phase angle difference, for if we downsample to 100 frames per second for the synchrophases, we're counting 21 frames. We're not counting 200 milliseconds, we're counting the frames. And so, yeah, we established our own pre-processing block essentially that would monitor the incoming synchrophaser streams, and then when it would tell our anti-aliasing logic or our overvoltage logic that there was a new frame for it to process. There was no free running timers. It was, you've got a new frame, look at the frame, process it, increment your counter, and then you wait. So in the background, there was all the processing of, just managing those synchrophases ourselves. So I guess that was kind of the nuts and bolts of the implementation, the more nuanced implementation of how we do our anti-aliasing and our manage the synchrophases. Being what it is, standard implementation, it is essentially a drag and drop, plug and play function for us now. So anytime we need an anti-aliasing scheme function, it's the same implementation, same logic, same function blocks, change the inputs, and the rollout becomes a lot faster. So moving on, just to give you an idea of what it all looks like in the end. So these are some of the performance results. So for our fastest overvoltage element, it's understanding what the inherent delay is and using synchrophases as well. So if our synchrophaser delay is 60 milliseconds for the overvoltage element, the actual operating time is about 70 milliseconds slower. So you take into account your comms latency and so on. Some quick conclusions. So there's advantages and disadvantages of using it. It's low complexity, it's modular, but it is a bit slower than what you may typically like. We've got approximately 9 synchrophaser-based anti-aliasing schemes out there now, and we've had 2 in-service operations. So if you're developing your own applications, there's considerations to be made in managing synchrophasers, which may be application-specific or device-specific. And then understand the inherent time delays that may exist if you're trying to implement protection schemes. That's it, thank you.
Thank you for that, Daniel. I realize that we have very short time frames, so apologies that you had to rush through your presentation. Our next presentation will be by Mohammad Zakir. and it's on TAS networks experience and applications on synchrophases. Mohammed is a protection and control engineer working in TAS Networks Asset Engineering Secondary Team. During his time at TAS Networks, he has worked in design of protection and SCADA greenfields and brownfields projects. He has experience in testing and commissioning of secondary equipment, protection setting, design and condition monitoring of substation equipment. He has an interest in protection systems, SCADA systems, and equipment performance. Please welcome Mohammed.
Thank you, Anita, and good morning, everyone. So today I'll be presenting on behalf of TAS Networks. So the basically I'll just tell you guys if you don't know TAS Networks. So we are a transmission and distribution utility company, operate in beautiful island of Tasmania, and like it's a state, but it's an island in Australia. So our network is spread over like 220 kV, 110 kV, and in distribution we are doing 33 kV, 22 kV, and 11 kV. So there is quite a lot. Today I'll be explaining from end user perspective about the applications of PMU and our experiences and how we are going forward with PMUs in future. And also I'll just give one example, a case study example of an islanding scheme, anti-islanding scheme for the PMUs. So yeah. Yep. So there has been a challenge for everybody probably with increase of IBRs, investor-based resources. We have been having non-synchronous penetration in our network. This is one of the snapshot from PMU data, which is telling like 80% of the generation from in TAS networks is non-synchronous penetration. So if it's a good windy day and we are using wind farms and lesser load is required, and maybe like we have a Basslink from Victoria that's providing us 500 megawatts, we probably don't need any synchronous generation to help run our network. But what it does is like it decreases the inertia of the system, and yes, it impacts the system stability. Now this is one of the major issues which probably we'll continue to face with increase of PV to be embedded in our network as well in future. So with this makes importance of PMUs like furthermore. So what we use is like we have been using data from PMU to see and analyze how much non-synchronous penetration has been in our network, and then we use synchronous condensers to introduce inertia in our network. Apart from that, we have been utilizing PMUs for monitoring the compliance of generating systems, also to monitor our wind farms who go their fault right through behaviors. So basically, if we encounter a fault, we need to see if a wind generation like is injecting the reactive current during that time, or it gets desynchronized from our network. So it's really important to get that visibility, and that high resolution data from PMU helps us to give us that visibility, and then helps our system performance team to just act accordingly. Apart from that, we have had seen incidents where we have distribution faults, and that has sent our wind farms into FRT. So it's really necessary and critical to keep monitoring this using high resolution PMU data. Secondly, we'll move towards slide 3. Yes, so apart from these applications, we have been using PMU for our protection schemes. That's implementation of anti-islanding scheme using PMU. This I'll be explaining as a case study in one of the later slides. Input to the state estimator. So this is a software. What it does is like it takes your data from PMU, which you have available, and it also takes the voltages which you'll have from conventional sources. It conditions it and derives more accurate voltages for us. So this has already been explained by some of the few speakers before. So that's one of the most common application as well. Apart from that, it helps us to analyze faults, post-fault behavior, and also do a system model validation. I'll quickly skip on to other slide to show you what topologies have been implemented at TAS networks from PMU perspective. So we have some stations with just one PMU and directly going to NOx PDC. And there are some areas where we have multiple PMUs. So if you have a multiple PMUs, you may need to have a PDC in your station as well. What PDC does is like it conditions the data, it adjusts the phasors and magnitudes, and also takes care of duplication of any data. So it becomes very important to have a PDC installed. Even if you have one PMU at site, we usually recommend to have a PDC installed, because if future PMU requirement comes in, I think it's pretty easy for us to integrate that way. There are some things that are happening in our we are working on for the future to develop a link with the market, but that's not done at the moment. Now there are multiple type of ways you can do PMUs. So you can have a standalone system. That's what we have. And you can have your protection relays just enable C37118 and utilize the PMU functionality in that. We are doing that as well. So we are using like cell 351 and 451s. These are the relays. These are the standalone PMU units. More processor speed because they are dedicated ones. But it's kind of an expensive deal for a utility. We have to just spend 10 to 15 grand over it in order to implement it, while the other one is just utilize the relays which come with PMU card in it, and what it does, it's just a comms card, just activates C37118. So now we have like moved towards in that direction, that if we are commissioning a new bay, something new is coming up in the project, what we have started to do is, in order to have more visibility of synchro phasor data, what we are doing is activating the PMU stream in these relays. This both comes, so there are probably all the vendors are supporting this stream. Currently we are using GEL90, confirmed from Siemens as well. They have this functionality as well, and the classes are configurable, so you can do even M class and P class. We in our network are doing P class, which is more fast. It's a protection class PMU, while the M is a measurement class, which gives you more higher resolution. Let's move towards, so I'll just clip over this slide because probably due to the shortage of the time, but that's the Tasmanian map. The red dots are showing the installation of PMUs in our network there, while the other blue dots are the ones where we have planned the installation. Let's quickly move towards the anti-islanding scheme. So there's this anti-islanding scheme. So Muscle Row is one of our wind farms that's connected to our network through Derby substation, and then it connects to the network. So what we have done in order to implement the anti-islanding scheme is have PMUs at Derby, where it's connecting this Muscle Row wind farm, and then there is a PMU also at Headspin substation. What we are doing is we have installed a synchro vector processor. It's taking the input data from both of the PMUs, calculates the voltage slip, and what it does is if our network gets desynchronized, that means there will be a voltage angle shift at Derby, and we'll just strip off the wind farm. So this is how we are implementing anti-islanding scheme. The next slide gives us an overview of. Can move to the next slide. I'll do that. Yep. So this is how we are doing that. So it does involve a PDC synchronous vector processor. Now cell 33778, this is no more available in the market. Now they have recommended to use RTEC with SVP library. Apart from that, the PMUs, I've already mentioned those. So before the time runs out, I thought I'll just go through one of the case study which happened. So we had like 3 trips in August 2020. We weren't able to know what was the reason of the tripping. After some root cause analysis, we used a contractor to help us out in that. We figured out that the time clock that we were using, it failed. So there was a glitch, and what PMU did, it utilizes the wrong time sample, and it evaluated due to angular phase shift, it will tell you separate voltages at one time, while the other instance, like the PMU at Headspin was seeing something else, while the Derby was seeing something else. So it caused mild tripping. Now, the question, like we were thinking that if there is this, if the data is corrupted, it shouldn't have been like, picked up by PMU. It should have been declared as a like error data. But as we know that we use parity bit for IEEE, like time error detection. But when we talked to the manufacturers, they told us like if the parity bit remains the same, so if it's an even parity in the sender frame and in the receiver frame, if it's again a even parity, we won't be able to detect it. So yeah, so this was one of an issue, and then we were recommended to have clocks, IRIG-B clock replaced like in 10 years to avoid these situations. But yeah, that was one of our experience. I thought I'd share. Future steps, this is just what we are planning to do. We want to use PMU data for real-time voltage stability monitoring, FCS metering, and utilize in distribution. There are like Noja RC20 reclosers, which we have in our network. We are planning to install more to have more visibility what's happening at the distribution side. We can even monitor temperature of a line, real-time one, because we can monitor real-time impedances. Using that, we can just just use an algorithm to figure out what the current temperature of a transmission line is. So there is a lot we can do using PMUs. Yep, we are looking forward to that. Thank you so much for your time. That's it.
Thank you, Mohammed. So for the next presentation, we had a bit of a change of plan or program. The presenter for this topic was not able to be here physically, and so we will be playing back the recording of the presentation that was prepared, and the slides. We will have the slides with a recording. So the topic is applications of synchrophasers to distribution networks and evaluation of a grid-scale data acquisition trial. The presenter would have been Martin van der Linde, who is the general manager for marketing at Noja Power. So can we have the...
Hello, ladies and gentlemen, and thank you for joining for this brief presentation on the applications of synchrophasers to the distribution network. Over the past few years, Noja Power has been involved in a project which was, at the time, the world's first large-scale application of distribution synchrophaser technology throughout the medium voltage grid. And this project was to trial and see what applications could be seen from empirical data gathered in the field based on the real-world data that we saw from the various installations. This project was a partnership between the Australian Renewable Energy Agency, Alternate Services and Energy Queensland, along with research partners in the University of Queensland and Deakin University. We were also joined by AEMO, who were very interested in the project as we move forward. The key goals were to use the data and technology to safely and reliably lower the cost for DER connections to the medium voltage network, and really to accelerate the transition to a sustainable energy future and improve system planning under high renewable penetration. Now, a lot of these technology capabilities, as you've heard from the previous presentations in this section, claim that these are possible, and at the time all that we had evidence to support that was from the transmission space as opposed to the distribution network. So this project was to find a way for us to gather the PMU data from the distribution network in a cost-effective way, and then provide that to the researchers and AEMO to find if we can achieve these key project outcomes. Required performance in order to meet the PMU standard is quite arduous, and so there was a considerable amount of research that went into understanding whether the existing assets on the distribution network would be able to achieve this. On the right-hand side there, you can see a couple of graphs which show the required performance of less than 1% total vector error. And there are three different variables that impact that, being magnitude, phase angle error, and the timing error. So those graphs show the tolerances available in the other two domains if you hold one of them constant. So if your magnitude error is 1%, then you are allowed 0 phase error and 0 timing error. Same if you have timing error of 31.8 microseconds at 50 hertz in either direction, then you are allowed 0 magnitude error. So the implementation that was required to meet this was very arduous. And a lot of the research in the initial component of the project was to do this. Now, the idea was hatched that we could partially use the existing overhead distribution network protection assets to gather this information, specifically pole-mounted auto reclosers. Many pole-mounted auto reclosers that are installed in the field today already have the primary sensors that would be necessary to do this. However, there would have to be an improvement in the technology, the controllers that were attached to those. And so it was decided earlier on that we would enhance the recloser controller that was attached to integrate a PMU capture into that new generation of recloser controller. So we boosted our sample rate up to 12.8 kilohertz from the existing 32 samples per cycle in the legacy products that are in service today, and implemented 10 times the processing power that we saw in the prior generation product. And that was to handle the high level of data input that was required, or data throughput, as the PMUs were generated around the network. This also allowed us to increase the power quality monitoring up to the 63rd harmonic, which was also of interest to network service providers, as the intention was to connect more renewable energy to the distribution grid. And so the integration of the GPS system, and with the completion of the ARENA project, the integration of the PMU based on that GPS capability and the improved sample rate, gave us the hardware fundamentals. What this meant was that for some of our partners, they could use existing high voltage assets and simply replace the controller in order to gather the PMU data from their existing network base. And since that was not a high voltage operation, it could be significantly more cost effective to gather this information out in the field. Equally, we also implemented a phaser data concentrator system. So this was a VPN connection from the devices in the field through the utilities IT system, which was then hosted on what we called the Noja Power Analytics Cloud, where the data was warehoused on Microsoft Azure, and the access to the data was granted to the NDA signed secure project partners. Now, we used various tools in order to build that technology stack that allowed us to get some visualization of all of the phaser data that we gathered across the distribution network. And so for the latter half of this presentation, I wanted to go through a few of the application outcomes that have been derived from the research from this data that was shared with our NDA partners. So firstly, state estimation today is an important part of managing a distribution network, and the PMU data that we gathered allowed us to provide really state measurement as opposed to state estimation. So by gathering the information with all the phaser information at the different points on the distribution grid, you can calculate your impedance values all over the network, and that gives you higher performance for your network state estimation, and also gives faster results because it relies on less computation. It's more relying on additional empirical data that you gather. And so we can see an improvement in the quality of the state estimation of the distribution grid. Another outcome was an increase in the grid's capacity for renewable energy generation. Today we use conservative limits to stay within the voltage stability index, but not all feeders that are connected to the distribution grid are operating anywhere near their maximum loadability point. And so in general, using the synchrophaser data that we gathered, we can calculate an accurate distribution network voltage stability index on a feeder by feeder basis. And so this sets a data-driven safe limit for renewable penetration on a per feeder basis. With this information in place, as more renewables added, that synchrophaser data then provides real-time monitoring to ensure that the operating of the point doesn't approach the maximum loadability point. But all of this gap that we see here is still available to load more renewables onto the distribution network whilst equally managing it. So a high instability index shows a high consequence for those faults, and so it is important to stay within a safe realm. But by having the high resolution data capture on the distribution grid, you can make these decisions based on the evidence that you see on the network rather than relying exclusively on modeling that we see. And so ultimately, it allows your operators to monitor for that stability under different network switching topologies too. So if you have more than simple radial feeders, when you connect the network in different ways, this will affect the loadability of those feeders. And accordingly, when you then measure the synchrophasor data, you can get a better indication for what that maximum loadability point is. Another outcome that we saw was the ability to predict equipment failure. So more specifically, the PMUs were capable of detecting insulated flashover and partial discharge around the network. Now, this will further require implementation in a real-time system, but a machine learning algorithm was designed to flag this condition based on learning from the data that we saw and was gathered. And so it detects faults previously missed by conventional protection, and it also provides the ability to prevent or do preventative maintenance rather than relying on a future outage in order to indicate there being a fault. And so stage 2 implementation was to add this to a analytic system, and some of our utility partners have progressed that implementation over time, still relying on the information and the data that is gathered from these RC20 devices. We also managed to detect faults that would normally be missed by conventional protection, and again, this is another case of using the machine learning to process that synchrophasor data. The best way to do this is if you can correlate the information from your existing fault data and then correlate it with the data that you gather from the PMUs in order to train your own model to detect these various cases on the distribution network. And so it gives us precision and confidence in making recommendations for fault site locations as well. So it provides additional information that you would normally not get from conventional implementation. When you have this sort of high resolution data being captured on your network all the time, it provides a wealth of information in post-fault analysis. Effectively, you've got samples being taken with GPS timestamps across your entire network, so the ripple effects of any major outages or any major faults, or even minor ones, could be seen all over the distribution network. And so it's an exciting time for this data implementation. As we're seeing the improvements in our capability to manage large data sets, we'll start to see more and more of this technology rolled out. And in the future, we anticipate that seeing more devices like PMUs integrated into recloser controllers is going to be a common way to access this data and to harness the power of the data on your distribution network. Thank you very much for your time. If you have any questions, you can forward them to the email address that's on the screen there. Hope you enjoy the rest of your conference.
We thank Martin in his absence for his presentation. The last presentation for this session will be Transpower's New Zealand's synchrophasor-based SyncCheck auto-reclose application. The presenter is Peter Bishop from Transpower. Peter has over 30 years of experience in power system protection engineering, support and management for a transmission utility as well as a protection manufacturer. His experience includes protection operation and application analysis, setting studies, simulation and testing, training, investigations and project support. He's presently the convener of SEGRE Australia's B5 Protection and Automation Panel. He's a co-author and presenter of 4 protection conference papers and SEGRE convener and co-editor of the B5 Green Book, IC 61850 Principles and Applications to the Electric Power System. Please welcome Peter.
Thank you. Yep. So thanks, Anita. So basically I'm a principal protection and automation engineer with Transpower New Zealand Limited, and this presentation summarises Transpower's application of a synchrophasor-based auto-reclose synchronism check scheme for helping to restore supply after faults. First, some New Zealand context on the need for this application. Transpower is responsible for electric power transmission in New Zealand. It provides, operates and maintains the high voltage transmission circuits and substations, traditionally connecting large grid-connected generation to large loads. However, more embedded generation is being connected. After power system faults, Transpower generally require a time-consuming line patrol to check for causes such as dangerous joint failures before manually closing the circuit back in. Auto-reclose of transmission circuits has become more important to promptly maintain supply. Depending on grid configuration, the grid and embedded generation may become separated following a fault. Reclosing onto generation may cause high currents and damage unless measures are taken, such as applying synchronism check and anti-islanding before auto-reclose. A problem with traditional synchronism check schemes is that it is dependent on many voltage transformers being installed. I will describe the stages of Transpower's traditional scheme. First, circuit breakers at each end of the transmission circuit open following a fault. Then, a three-phase line VT at the same end is used to check the line is dead to allow the system end circuit breaker to close and charge the line. Then at the non-system end, line and bus VT voltages are compared for synchronism. If synchronism is maintained, the non-system circuit breaker is closed to restore the circuit. For this traditional scheme, a combination of bus and line VTs are required at each end of the circuit. The problem is that most Transpower 110 kV line circuits lack line VTs. Bus VTs are standard. A synchronism check scheme is generally only added where required as part of a line protection upgrade, and this traditionally would involve installing line VTs. However, with more embedded generation, a synchronism check scheme is required more often. With additional protection in VTs, there is significant cost and effort. An alternative solution is to use a synchrophaser synchronism check scheme. Voltage signal transmission is via a separate synchrophaser communication channel. A separate protection signaling channel is also used for permissive voltage checks due to the slow data refresh rate of the synchrophaser channel. It therefore requires only three-phase bus VTs at each end of the circuit. A synchronism check is made at both ends of the circuit, and the open interval is staggered between the grid and non-grid ends. The scheme uses synchrophasers and high-speed communication channels. I will briefly describe its implementation in Transpower's initial design. Synchrophaser protocol is used to continuously transmit bus A red phase voltage, phases and frequency information to NB. Relay B is continuously using the received data together with bus B voltage information to determine whether an asynchronous condition exists. If bus A is in synchronism with bus B, then relay B will send a permit auto-reclose signal to relay A. Circuit breaker A close is then allowed. This is used instead of a deadline charge. If bus A voltage is healthy and balanced, relay A will send a permit auto-reclose signal to relay B, and provided bus B voltage is healthy and balanced, circuit breaker B is allowed to close. Following a fault clearance and at the end of the auto-reclose open interval, circuit breaker A will close if the voltage is still healthy and balanced and it's received a permit auto-reclose from relay B. Similarly, at the end of the auto-reclose open interval, circuit breaker B will close if synchronism check conditions are met and bus B voltage is healthy, still healthy and balanced, and it receives a permit auto-reclose from A. System studies can be used to adjust the open interval and take account of transient voltages and swings. The synchrophaser synchronism check scheme has now been implemented at a number of sites. There have been a number of successful operations where synchronism check has allowed auto-reclose to restore the circuit. One such case is illustrated in the slide for the Corridge to Hororata circuit. Where there is a weak circuit to Corridge and the west coast with some local hydro generation. A red phase fault occurred, then the circuit auto-reclosed after checks showed small and allowable voltage angle difference, voltage magnitude difference, and zero slip frequency. In summary, with more and embedded generation, there is a greater need for synchronism check associated with auto-reclose. Synchrophaser synchronism check systems save effort and cost. The scheme has been developed since the initial design and has now been deployed and implemented over the last few years. System studies may be required to calculate some setting parameters, particularly for voltage transient conditions. Synchrophaser values cannot be compared with real-time values, so the scheme relies on signal alignment and dedicated logic. It also relies on both healthy synchrophaser and protection signaling channels. This implementation avoids adding two sets of line VTs. Synchrophaser auto-reclose is now a standard transpower method for synchronism check and has an associated standard design. There has been early positive experience with successful auto-recloses. Transpower continue to monitor and apply the scheme. I would like to reference and acknowledge the associated CPAC 2017 paper by David Chen and Peter van Dyk. Thank you.
Thank you, Peter. You would have noticed that the format of this tutorial is quite different to what we conventionally have as a tutorial, and it was intentional. I think there was we reckoned as the tutorial advisory group that there would be interest in seeing the applications that have been deployed across the region. You have got a taste for what is out there. Unfortunately, we've also run out of time, so we won't be able to take many questions. I would like to possibly take 2 or 3 questions from the floor, but what I would recommend is that you know who the presenters are, and I would suggest that during your break that you touch base with the presenters if you have further questions for engagement. So if we could have a question there.
Check. I have a question here.
Okay, go ahead.
I'm Satyendra from Tax Network. The question is for general panel, but more specifically from James from AIMO. Like as James said that they're getting streaming synchrophaser streams from different utilities across in the NEM area. So from your point of view, do you see any concern or do you have any comment if the synchro phaser streams are coming from the IE protection relays, which generally are fed from protection class CTs, not from dedicated metering CTs? Because in my opinion, a reasonable PX class CT is reasonably good in terms of operational metering as well. So that is a big thing for us, like to get best bang for your money. Like we would like to stream through our protection relays, the synchro phaser data. Thank you.
Yeah, thanks. Thanks. It's a very good question, and it's something that we've actually had a lot of discussions with the NSPs over whether to use metering or protection class relays. And what we landed on was that ideally we'd like metering class CTs if they're available. However, we would accept protection class CTs, given that most protection class CTs these days are comparable in accuracy to the associated metering class CTs. So we allow either, but preferably metering if they're available.
Thank you.
Yeah, hi. I have a comment and question. Several of you have spoken about the sync check angle, and on several of the slides, I see 20 degrees, 40 degrees. Now, with so much generation retiring and so much IBR penetration, like task networks showed that SNSP, high penetration, PowerLink touched on it, and even the last presentation from TransPower, you were showing 20 degrees. 20 degrees is very conservative, I think. So can you please comment on this with the system becoming weaker with less generation as your X is increasing, your angles, you will see larger phase angle changes, and there is penetration of grid forming IBR. So there is overall a question about the stability of the voltage waveform. So what is acceptable? Can we just keep going 40 degrees, 60 degrees in the context of IBR? Can some of you comment? Have you seen large phase angle changes in real-time operations? Have you come across? So how do you handle that?
Yeah, perhaps I could start off. Basically, with Transpower, we've traditionally used 20 degrees based on our existing systems, but I think there probably is an opportunity to explore that, particularly with IBRs and increased penetration. It's a good point. I haven't dealt with that directly, but I think there is in terms of exploring that further in terms of the setting. But I don't know whether there's any other comments from other utilities.
I can't comment specifically on why we use that setting, but essentially it's a result of the fault studies that our planning team run or are able to run. I expect at some point in the future, as we get more and more, those settings can possibly be refined. And I believe at the time it was specifically playing a bit safe.
Good question.
Yeah, thank you. Ahmed here, PwC Northern Territory. The fact that we're talking about PMUs and we're talking about diverse amount of data, so from phasor magnitude, angles to voltage to currents, etc. And the fact that we're talking about high sampling, up to 60 samples per second, so we're talking about massive and large amount of data. Every one of you talked about different use of the PMUs. What I'm interested in from real-time perspective, and I would like to see that thoughts of that. We're talking about large data to be processed, transmitted, and stored. We're also talking about a large amount of data that will need to be analyzed and presented in a visual-friendly format to the operators, like us in the control room. So what's your thought about tackling these two challenges from data storage perspective, and obviously having an effective methods to present that data so the operators doesn't get overwhelmed with alarms and signals and massive amount of data to make that decision?
Yeah, excellent question. Something on everyone's minds, particularly the storage part. AEMO, we've sort of taken two different approaches. We've split it into two categories. We have the operations and we have the offline stuff. So starting with the operations, that's fairly simple. You don't really need that much storage. A couple of weeks maybe just for looking back in time, trending, but the operators would rarely need to go back in time that far. As for processing power, we've found that, yes, it is a lot of data coming in instantaneously, but compared to something like, video streaming or something like that, it's not a huge amount of data yet. It could conceivably, but at least in our projection, we don't see processing being much of an issue for the near to medium term. Then the question becomes on, offline use of the data and storage of offline. And really that's something that the organisation has to settle on, because you can store as much or as little amount of data as you want. So at AEMO, we sort of sat down with all of the teams and we sort of came to the agreed upon approach to store it for X number of months, rolling window, X number of months, with also having event data. So event triggers like under voltage, under frequency, etc., that being essentially stored permanently for that 4 or 5 seconds, 10 seconds, however long around that event. So you've got your continuous rolling window of the several months. You've got your event-driven data, which will be stored indefinitely. And also, just for compliance and things, we've also decided to have a select number of PMUs, maybe on the order of 4 or 5 PMUs across the entire NEM, to be stored also indefinitely, continuously. So that is something that we've had to think about, but there is always going to be compromise, and that's sort of what understanding the requirements of the business is crucial to determining that.
Thank you. I think I'll take the last question there.
Can I just add something?
Sorry.
Just to echo James's comments, so with Electronet's use case, again on the WAM side, there's different repositories that you can create as the user. So there's long-term storage, short-term, which would probably be at full resolution, and then there's snapshot events where they're the important ones that you want to trigger and store for I guess post-fault analysis. So you get some control of shaping the storage requirements.
Yep, thank you. Michael Guy from CT Lab. The question is probably for James. When you're looking at subsynchronous oscillations, you've stated that you can go to 25 hertz, which is the absolute limit. Is there any need to look beyond that? Have you seen any phenomena of that sort in the field?
It's an unknown question. We still don't know. You don't know what you don't know. And from our experience, and this is purely just from experience in both analysis of these types of oscillations, but also extensive electromagnetic transient modelling, what we've found is that the root cause of these oscillations, if you dive into the theory of the controllers of grid following voltage source converters, the instability, you do your Nyquist criterion, you get your eigenvalue analysis. The frequency of those oscillations is in the subsynchronous range, in 5 to 25 hertz for the current technology. There's not to say that new technologies could come along that bumps that frequency range up. But we sort of see that as then becoming more of a power quality issue rather than a system security issue. But it's not to say that it couldn't become an issue. That's when we are also investigating uses of things like high frequency PMUs, so PMUs that can record at 200 hertz, and also, as Vlad mentioned earlier, the development of waveform measurement units, so streaming waveforms in real time.
Thank you.
All right. I do realize there are more hands, but we are closing the session at this stage. I would like to take this opportunity to thank all the presenters for the work they put in. And thank you to you as the audience as well. I see it's quite a full house, so there's clearly a lot of interest. Please do engage the speakers during your breaks for the questions that you may have. Thank you.